Hey everyone, welcome to Kristoffer's talk on package extensions, a new language feature. I'll let him go ahead and start off. Thank you very much and welcome.
Thank you. So welcome everyone. As been said, I'm going to talk a little bit about a new Julia feature, which is called package extensions. But first I want to give a little bit of background. So first I want to talk a little bit about the cost of adding a dependency. So if there was no cost, we could just add a lot of dependencies, but unfortunately that's not really the case. So one cost is the download size. The packages themselves tend to be kind of small, so that's not a big deal. But some packages have big artifacts, like they depend on MKL or CUDA or something like that. Another one is what I call bundle size. If you're creating an app or a library with package compiler, you have to sort of stuff everything you depend on in there. If you want to ship that to, let's say, a customer or something, if you have a lot of dependencies, that might be a very big bundle. Another one is maintenance load. If you have a lot of dependencies, maybe they release breaking changes. You have to be aware of that. Pre-compilation time is another one. It only happens once sort of per version, but still, if you have a lot of dependencies, pre-compilation time can be significant. Then load time, I put that in bold text here because I think maybe that's the most important one, or the one people care about the most. It's just if you have a lot of dependencies, your package is going to take longer to load. So as a package author, you kind of have to balance this thing of the cost of adding a dependency, but also the sort of the usefulness of having a dependency, because typically by adding a dependency, you get some more features or maybe a bit more performance, or there's some reason you're adding a dependency, so there's a benefit there too. So then you end up in the discussion about sort of the value of dependency, like is it worth the extra load time to add this dependency? And there's a little bit of a point of contention there where, depending on who you're asking, some people might say it's worth it and some people might not say it's worth it. So why do we depend on a package at all? And I would say in Julia there's sort of two main reasons. The first one is you want to directly use the functionality of the dependency, and this is what I call a strong dependency. So as an example, the package manager, it directly uses the TOML library to write out the TOML files. The package manager wouldn't work without the TOML library. It's a crucial thing to be there. You could have a nearest neighbor search in some kind of machine learning library. So that's one reason why you would depend on a package. But the second reason is a little bit different, and that is you only want to extend methods to types in your dependency. So you want to provide a bit of extra feature, but you're not actually using that dependency directly. You're not calling into that dependency. And this is what I call a weak dependency. So an example of that could be, for example, static arrays in forward diff, where forward diff accepts a static array as into its gradient method, but it doesn't use static arrays itself in any way. It just accepts something. You could have a plotting package that adds support for intervals, for example, so you can have plots with intervals. The plotting package is not using intervals, it's just accepting support for it. Or you can have many numerical packages that add supports for automatic differentiation rules, which is quite common. So one observation for these weak dependencies then is that these extended methods can only be called if some other dependency have a strong dependency on that one. Like someone has to actually use that thing in the end, otherwise it's not used. So if we have a package that's not used by any other sort of totally strong dependency, then it's not actually used at all in your program and it's not needed. So to give a concrete example, I put some sort of one possible dependency graph here, and I have B and C are dependencies of A and so on. And here I have different colors for the sort of different dependencies here. So B here would be a weak dependency of A, and D would be a weak dependency of B. But then we also have strong dependencies. So E is a strong dependency of B. So that means that B here is actually using things in E, but it's only extending stuff in D. So there's two sort of types here. And just to have a bit of terminology here, I already said about the weak and strong dependencies. And then I also just say that A here is a parent of B and C. I mean, I could also say dependent, but if I say parent, it's pretty obvious. If you think about this as sort of a relation diagram, this is the parent of B and C. And then we sort of have the extension code, what I call it, which is the code here that extends. So this would be B extending some code in D here. So just to get some terminology. And then we can sort of start coloring these dependencies if they are totally weak or totally strong then. So we can have some rule here that the top level dependency is totally strong. I mean, you can always call into your top level dependency. And any strong dependency of a totally strong dependency is also totally strong. So C here is a strong dependency of A, and A is totally strong, so C is going to be totally strong. And if you're not totally strong, you're going to be sort of what I call totally weak. And the point then in the end is that everything that's totally weak here is not actually callable and is not used at all in your dependency graph if we are ignoring stuff like type piracy. So in the end, we can sort of just remove them and it's not going to change your program behavior. So in this case, we went from 8 to 4 dependencies in our dependency graph, and that could of course be given some load time savings. So what information do we need to give to be able to sort of do this thing? Well, we need to mark a section of code, I call the extension code, to be executed or loaded, conditioned on the loading of another set of packages in the current Julian session. So if you want to implement this, you have to sort of decide where do you store the mapping of these set of other packages and to the code that's going to run when they are loaded. And how is this code actually going to get loaded? And then some surrounding infrastructure, you might want to set compatibility on these weak dependencies. So even if you're not depending on them directly in a strong sense, you're still going to extend their methods. And so you're still sort of vulnerable to compatibility issues. So one way to do this is with the requires.jl package, which has been used for a very long time, and it's done a very good job in sort of solving this problem. So in that case, you add requires as a dependency, you load it, and then we have a section of code here, which is in blue. So this is the section of code we want to run, conditioned on that, in this case, gadfly is loaded. So we have a set of other packages that we sort of want to load, which is gadfly. I call this a trigger because it triggers the loading of this code here. So the mapping then between the trigger, which is this, in this case, gadfly, and the extension code is defined inside the package with the macro here. And the way this actually ends up loading is that this macro acts a callback. And whenever gadfly gets loading, it's going to evaluate whatever code is in here into the package. So that's the way sort of requires work. There are a few drawbacks though to required. So one of them is that the callbacks are added by actually running Julia code in an init method. And sometimes this code can be invalidated, so it has to be recompiled. So that gives a bit of extra latency. This extension code is executed with what's virtually an eval call. So this means it's hard to cache this compiled code. So the code that's here is going to be evaluated every time Julia starts. So it's then hard to cache it. So you have to compile it every time. The extension code is often defined in a separate file that's loaded at runtime. So many times, instead of having the code there, there's an include statement with the file. But if you're using a package compiler, you're just kind of bundling all the code, and then you don't have, maybe the file does not exist anymore. So another thing is revise does not work with this thing. So if you change the extension code here and you have revise loaded, it doesn't update. And another thing is, it's not a direct requires issue, but it was an issue with this whole thing, is that there was a lack of surrounding infrastructure. So you couldn't enforce compatibility on weak dependencies. And so yeah, that wasn't so good. So the alternative then is what I call package extension here, or what's called package extensions. So again, as I wrote, we have to mark a section of code that's going to be triggered on a set of other packages being loaded. So the question is, where do we do that now? Well, the alternative here is that we do this in the project file. So in the project file, we can add a new section, the weak dependencies, and here gadfly is in. And then we're saying basically we want a file to be loaded when gadfly is loaded. And we can also now add compatibility on this. So the way this would work is a little bit different from requires. So in your package file, you would have, just as an example here, you have some abstract type. I call it display type. Then we have some, this is a textual type maybe, or a graphical type. And then we have some type, and then I define that, okay, my type is a textual type. But then I can also add this extension. So in an extension folder, I create this gadfly extension file. And in that, it's a module. And then I do the extension of my function here with the gadfly plot. And that one is a graphical type. And since this is a separate module here, the extension code, it allows it to be precompiled just like if it was another package. So you can precompile it, and it also works, revise also just works with if. So if you would change this and have revise loaded, it would change straight away. So in practice, how this is used then, so let's say if I load my package here, then I can call this function on my type, and I give the textual here. So this is just this code here that's getting executed. But now if I also load gadfly, then behind the scenes, the extension gets loaded here. And now if I create a plot object, and I call my function on this plot object, then because we extended my function here to a plot, we get the graphical in there. So what extension is typically used for, you can add optimized version of function for certain types. So if someone provides you a static array, maybe you can do a bit better than if someone provides you just an array. You can sort of add some kind of plug-in behavior where you add things like automatic differentiation to your functions, or maybe you want to add some plotting capabilities to different things. And I have a real-world example here where I have a plotting package that wraps PGF plots, which is a sort of a LaTeX plotting system. But this one uses a few extensions. So if we go down, we can see we have some weak dependencies and some extensions. And if we go back and look in the extension folder, we have the 4 different extensions here. And just go into one of them. It's a separate module, and then we start overloading things inside the package based on a type here that's inside this trigger then. And then we have one for colors because we want to be able to plot with different colors. We have contours and some stuff in stat-based and so on. And what's nice about this is that if these triggers are not loaded, then it's basically free. This code doesn't cost anything unless someone actually loads these packages. So if someone wants to add support for some other type here, there's no real reason to say no to that because it doesn't cost anything unless someone sort of actually uses it. There are a few differences between requires and package extensions. So requires evaluates code into the package module, while package extensions have things in a separate module. So that creates a little bit of a difference here. And one way I usually think about it is the loading of the package extension module is pretty much equivalent to loading a package that depends on both the parent and the triggers. So if we look at this code down here again, when this extension is loaded, it's effectively like someone had created a package that was called gadflyx that depending on my package and gadfly and had this code. And then you would write using gadflyx. That is sort of exactly how it works behind the scenes. So that's sort of a good way to think about it. And there are some restrictions to what packages can do at precompile times, and that also applies to these extension modules. So you cannot evaluate code into the parent during precompile time, and you cannot really set new symbols into the parent. So what some people want to do with extension is they want to sort of add a new symbol, parent dot something, that sort of appears as soon as the extension is loaded. But that does not really work, but I'll show some sort of ways how you would do that instead. And since now the extension is in a different module, the question is how do I sort of get a reference to that module? Maybe I have to look inside there somehow as the parent. And there is this base.getExtension function where you can you provide a parent module and then the name of the extension. And it gives you either nothing if the extension is not loaded, or it gives you the module if the module is there. And just as a little like best practice thing, I guess, I don't think the extension name should be exposed to users of the package. That should probably be kept internal to sort of the parent. That's sort of, I think that's a good idea. But this feature is new. I mean, so saying best practices is a little bit hard since we don't have so much experience with it, but that's just at least a feeling that I have. Another discussion is about backwards compatibility. So package extensions became available in Julia 1.9, but of course a lot of packages want to support 1.6 up to 1.9 because 1.6 is the long-term support release. So there are various sort of backwards compatibility strategies that you might want to do. So one example is that maybe before 1.9 you want to have a dependency as a normal dependency, but after 1.9 you want to have it as a package extension. Another one is that maybe before 1.9 you want to use requires because you used to use that and it worked pretty well. But then on 1.9 plus you want to switch over to a package extension. And the last one is that maybe pre 1.9 you don't want to load it at all, but then on 1.9 you do want to use it as a package extension. And I'm not showing the exact guide to do that here, but there's a pretty detailed guide here on the, if you go to the package pkg.jl documentation, there are like examples for how you would do all these 3 different backwards compatibility strategies. Like what you have to think about and what you have to put in your project .toml file and so on. Okay, so now I'm going to go a little bit to sort of more advanced usage. So what I've shown before is if you're using a package extension purely for extending a method, this is kind of known territory. It works well, and it's been quite a few packages that have started adopting this, and there hasn't been that much of an issue. And the example I showed with PGF plots there is exactly in that territory. It just extends some function based on some types. But let's say you have this case where you want to solve some linear system, let's say. So you provide a matrix and a vector, and then you want to be able to set, I want to use the hyper for the algorithm to solve this system. And you want this to work when hyper is loaded, but you don't want to bring on a full dependency on hyper. The thing here is we don't really have any type to directly dispatch on. We have A is probably a matrix, X is probably a vector, and this is just a symbol. So we don't really have a way where we can directly overload something. So a first case of doing this might be something like this. We have some kind of an abstract type here, abstract solver. Then we have a struct, I call it hypersolver, one of these abstract solver, and we maybe have other types of solvers. So here's Paradiso solver. And then we have this function solve system where we take in this matrix, the vector, and the algorithm we want to do. And then if the algorithm is hyper, we call this underscore solve system with a specific type then. And the point here is that in the extension for hyper that we want to do, we overload this underscore solve system with this specific type. So then when we call this, it's going to call the function extension here. And if that's not loaded, we have sort of a fallback here, which just takes an abstract solver here. So if we're trying to call with the hyper algorithm and that's not loaded, the extension is not loaded, we're going to end up here because this is going to be the best matching method. And then we give an error. It should be a better error message, but you need to load some package for this solver. So that would sort of be an initial attempt at doing this. There's one issue with this type of code, which I call the transitive dependency problem. And that is that your code should in general not depend on what dependencies your direct dependencies have. So if I'm depending on plots, and plot is depending on LaTeX strings, I shouldn't really depend on the fact that plots depend on LaTeX strings. I should only depend on my direct dependencies. But package extensions, they are loaded when all the triggers are loaded, but it doesn't matter how they're loaded, just that someone loaded them, then the extension code will run. So this code here will run and work even if this hyper package was loaded by some other random package deep down in the sort of dependency graph. And what can happen then is that this maybe this package that depends on hyper stops doing that. Then this code will all of a sudden break. So you have sort of inadvertently depending on what other packages depend on. So a possible solution here is to sort of, instead of passing a symbol here to the algorithm, you could pass the module itself, like you pass the actual hyper module. And by doing this, you kind of prove that you have a direct dependency on hyper, because otherwise you couldn't get an access to that module. So if we tweak the code a little bit here, so we have the solve system again, But this time instead, the algorithm is a module. And then what we can do then is that we take we get the hyperextension module here, and if that is nothing, and our algorithm is the same as the hypermodel inside the extension, then we're okay of doing this, because the user has sort of proved now that they have a direct dependency on the hyper. So if the API is like this, you don't risk that you're relying on what dependencies other packages have. So I would say that in generally, a good practice is that these extension method, they should ideally take either a type, which is sort of the normal case, or the trigger itself, or the module itself as an argument, because that's sort of the way you're proving that you have a direct dependency on this. But I'm sure there are cases where this is hard, but I think if it's possible, I think this is a sort of a good thing to do. So some results I have then. So let's first look at some performance numbers. So I have 3 packages here, which has been converted from requires to package extensions, or they were converted from using something as a normal dependency to an extension. So the first one is Zygote. So first, Zygote has had the requires usage that loaded different code. If you load a tracker, it had some things if you load colors and distances and so on. So what I first do is I load these things, and then when it used requires, we're loading Zygote, and then the fact that these are loaded means that the different requires code is going to run. And then it took 0.94 seconds, and you can see here that there's a significant compilation time. And then if we move to package extensions, and of course we restart the Julia session, we load these triggers again, and then we load Zygote, and then it was 0.4 seconds or less. So that was a bit of an improvement. We can also look at categorical arrays. They also had a few of these sort of conditional dependencies or triggers. So we load them, then we load categorical arrays. And again, we have a pretty large compilation time, and we also have recompilation. So what I think happened here is that loading categorical arrays or one of these sort of invalidated code that was used to run this requires code, and then it had to be recompiled. But when we use package extensions, we have these precompiled modules, and then when we loaded categorical arrays, it was pretty much instant this time. And the last one is forward if then. It used to have static arrays as a normal dependency. So when you loaded forward if, you also loaded static arrays. But as I said before, forward if actually never called into static arrays. It just allowed itself to be called with static arrays. So we can move that to an extension. And now it turns out that the load time of forward if was actually pretty much dominated by static arrays. So now if you just load forward if, it's a lot faster. And if someone loads static arrays as well, then you will still have the same functionality as you did have before. So there's no real loss in this transition between this normal dependency to an extension. And if we look at the total number of packages using this, it's 193 now since 1.9, so it seems to be quite rapid adoption. And as I said many times when I'm profiling package load time, requires stuff comes up as a little bit of a hotspot. And as I showed, changing to extensions quite often improve things, often not as much as in this cases. This is like probably the worst case for requires here when it gets invalidated. But usually it's pretty good. And so the hope is that package extensions will lead to like fewer number of strong dependencies on average, which means that your average dependency graph will be smaller and the average load time will be faster. But also to have much more weak dependencies, because weak dependencies is kind of what provides synergy between Julia packages. So as an example here, static arrays means that you have synergy between static arrays and forward if, and you have performance improvements due to it. So before there was a cost to adding these sort of dependencies, but now if you should just be able to add many, many weak dependencies without it costing a lot. So thank you. That was it for my presentation. And some questions.
Thank you so much, Kristoffer. Does anyone have any questions?
I was curious with extensions if it's possible for an extension to have a strong dependency that the parent doesn't have.
So the question is if it's possible for an extension to have a strong dependency that the parent does not have. So as an example here, the question is, can I do a using some other package here that the parent does not have? And the question is no, not right now, because there's not support for that in sort of the package resolver. The closest you can get is that you make a new strong dependency in the parent package, but you only load it in the extension. And the advantage of that is that you only have load time for that dependency when the extension is loaded. The drawbacks is that you still have stuff like pre-compilation, still have stuff like download size and so on. So you can do better than just making it a normal dependency in terms of load time, but in the other cases you still have sort of all the other costs. So.
I saw recently there was a package called Package Extensions Compat that was that's supposed to do the automatic conversion to requires instead of using this on versions that are older than 1.9. Do you know anything about that?
I actually didn't know that exists, but that sounds like a very good idea because I talked about these, that's right, the different backwards compatibility things, and you have to sort of add a bit of boilerplate to load things on different versions and so on. So if there is a package that allows you to do this automatically, then that sounds very useful. So it was called package extension compat.jl or something. Okay, so that I would try that out before doing this stuff, I guess, because this stuff is a bit manual, but maybe they have a nice macro to sort of automate the process. There's one over there.
Oh, what's your question?
Hello. Regarding that advanced usage, if those methods return different types, it will be type unstable. Is there a way to completely replace a function in the module if the extension got loaded, so that I don't have type instability?
So the question is something that if these things return different types, then you will have type instability. And if you can overwrite the method to help with that. You cannot overwrite a method because you're not allowed to overwrite method during pre-compilations. So when this extension is loaded and gets precompiled, if you overwrite a method, you're going to get a warning in 1.9 and probably an error in 1.10. But regarding the type instability, you mean if, for example, this function returns a different type versus this different? I mean, yes, you would have a type instability there, but I don't think it's. I mean, you're running you want probably to have the same thing pop out of solved system independently of the algorithm you're using. So maybe that's not a big problem in practice, because I guess you want to get out the solution B here, which is going to be probably a vector. So I'm not sure.
Thanks. This is really neat. It seems like a common pattern here would be basically in the case where one package provides, say, a function, and then another package provides some type, and you want to extend that function to dispatch on that type. And if these developers don't talk to each other, having the flexibility to do it however you want is great. But suppose that they do talk to each other, or in the limit of that, they're the same person. Is there a reason to prefer having that as an extension in one package versus the other, or should it not really matter?
Okay, so the question is, in which package should the extension go? So that is a good question, and I've thought about it a bit. There's not a direct way to figure it out, but there are a few things. So if you have to use the internals of some package, then it probably should go into that, be an extension of that package. Because otherwise, your extension might break if the other package does something. So that is one thing. So if I look at my real-world example here, and I go to the extensions, I'm overloading some stuff here. Like, I think this is kind of like an internal function to PGF plots X. So in theory, I could rename this function inside the package. But if this extension would live in the colors package instead, then things would break. So I think that's the one guiding principle is that, yeah, if you have to use the internals of some packages, it should go there. And if you're the same person having both of them, I guess it doesn't really matter where it goes. But sometimes it also just feels a bit like, it would feel a bit strange to put this extension code inside colors for some reason. I don't know exactly how to articulate exactly why, but somehow it feels better to have it in here, because I guess maybe this is a bit bigger package and it's just adding things for a bunch of different types that it's going to plot. The alternative is that the color package would have like a bunch of different plottings packages as its extensions, which sort of feels like the wrong place to have that, because colors is kind of a smaller thing.
All right, we're at time.
Okay.
I want to thank you so much again.
Thank you.